titled Algorithm Designed for Resource Management of Time-Critical Applications in an Edge Cloud Architecture. This was supervised by Associate Professor Arvind. So what is edge computing? So traditionally, cloud servers are massive servers that are found in faraway data centers. This increases the transmission time, and hence time-critical applications cannot be serviced by them. But recently, there has been the advent of Internet of Things, and along with it, the concept of edge servers or access points, which are smaller servers that are deployed close to end devices. Hence, transmission time is reduced greatly. So our motivation is to devise algorithms for time and safety critical applications, such that each task is produced by an end device has an associated deadline by which it needs to be processed. So what is an application example? Autonomous robots at a factory floor. They can be coordinated by sensors and actuators controlled by an orchestrator sitting at an edge server. Obviously, such an application is time and safety critical because if a mistake is made, then a factory worker could potentially be injured. Also, the recent advent of 5G wireless technology promises to reduce latency, and this can make such applications a reality. So, but there are obviously algorithmic challenges when it comes to resource allocation. So we need to develop efficient heuristics and hopefully algorithms with guarantees. So our problem formulation consists of tasks. Each task has 4 attributes: the profit, the deadline, data size, and CPU cycles. And there are 2 sets of servers that each task needs to be allocated to. So one server from each set essentially. So the first set consists of access points or edge servers, and they allocate bandwidth resource. The second type is cloud servers, and they allocate compute resource. So essentially, the total time to process a task is split between communication time and computation time. Communication time is given by the data size of the task divided by the bandwidth allocated to it, and computation time is given by CPU cycles of the task divided by the compute resource allocated to it. So once a task is offloaded to an access point, it is then sent through the backhaul network to the cloud server to be processed. So all in all, it takes 3 steps for the task to be processed, and there is time that goes in all 3 steps, which is the communication time, the computation time, and the backhaul transmission time. Overall, these 3 components should be less than equal to the deadline of the task. So essentially, we are solving 2 algorithmic challenges. One is the task mapping problem, wherein we need to choose exactly which servers are the task mapped to. And second is the resource allocation problem, wherein we need to decide how much bandwidth and compute resource exactly are the access point and cloud servers giving to each task. So this problem is NP hard. So we will not find any polynomial time optimal solution for this problem. The good news is that it is APX hard, so we can hope to find approximation algorithms with guarantees. So first up is the heuristic algorithm we devised. So we call this the zero slack ZHG algorithm. We devised it after 2 observations. The first is that if a task is executed exactly at its deadline, then there is no loss in profit compared to executing it much before its deadline. Number 2 is that if greater bandwidth resources are allocated to a task, then less compute needs to be allocated to it in order for it to be completed before its deadline, and vice versa. So the steps of ZSG are that we first enumerate all task, access point, and cloud server combinations. Then the algorithm based on heuristic formula splits the deadline of each task for each task, access point, and cloud server combination between the time taken for communication and time taken for processing. And based on this time split, we then calculate the amount of bandwidth resource that the task will be allocated by that access point, and the amount of compute resource that the task will be allocated by that cloud server. Then, given these values, we calculate the priority values for all combinations. The formula is given by profit divided by bandwidth times the computation resource. And then we assign tasks to their corresponding access point in cloud servers based on how high the priority values are and whether the following assignment is feasible. Then we devise an approximation algorithm. So approximation algorithms are algorithms that run in polynomial time and give a guaranteed solution that is an approximation of the optimal solution by a given factor for any instance of a particular problem. So a specific kind of approximation algorithm is a PTAS. Um, the definition of which is given. The good part about a PTAS is that we can tune the optimality of the solution for a PTAS at the cost of time of execution of the algorithm. So we have devised a PTAS for the discretized version of the problem and when the total number of servers is a constant. So what is the discretized version of our problem? It is defined as when the bandwidth and compute resources can only be allocated in multiples of minimum units instead of continuous allocation. And it is interesting to note that the multi-dimensional multiple knapsack problem is a special case of our problem. This implies that this problem, the MDMK problem, has a PTAS when the total number of knapsacks is a constant. This might be of interest to the approximation algorithms and algorithms community in general. So now simulation results. So to test ZSG or the heuristic algorithm, we generated 12,000 task sets with varying number of tasks, varying number of compute intensive tasks, varying number of percentage of bandwidth intensive tasks. Whereas the values for the access point and cloud servers remained constant across task sets. So in all our figures, in the y-axis, we have shown profit gain ratio. And these graphs have been obtained from our paper, which will from a paper written by Mr. Chuanchao Gao, myself, and Professor Iswaran. And this paper will feature in GlobeCon 2022. So I would request you to kindly notice the box plots for ZSG. There are box plots for the algorithms LDM5 and LDM15. They are not discussed in this presentation. So as you can see, ZSG in all scenarios at least covers 70% of the PGR on average. That is pretty good performance, even when the number of tasks increases or when there are high percentage of bandwidth intensive tasks or when there are high percentage of compute intensive tasks. So our conclusions are the following. So the strength of the heuristic algorithm is that it performs well. It achieves 70% PGR on average, and it can also scale very well. So it is well suited for large scale systems. Also, it is important to note that it does not require any special hardware. So it is very lightweight. Also, it has very fast execution time. And this is obviously an important feature for designing time critical cloud architectures. Now onto the approximation algorithm. So this algorithm is novel and it has a guarantee and its optimality can be tuned at the cost of time of execution. So for real world deployment, we suggest that the heuristic and approximation algorithm can be deployed together. First, the heuristic algorithm could be executed since it executes fast and does not use a lot of compute power. If it does not give a satisfactory solution above a minimum profit level, then one can resort to the approximation algorithm to give a guaranteed output at the cost of time of execution. And here I give the references for all the figures in this presentation. Thank you. I hope you